Today I'll be going through some trends in the lower food web, and we've had some discussion about this in the Lake Huron already. And I'll be stepping through things like the nutrients, phytoplankton, zooplankton, predatory cladocerans, diperia, myces, and quagga mussels. A lot of the data that I'll be presenting comes from NOAA's long-term research program located in southeastern Lake Michigan. This program focuses on relatively high frequency sampling from March through December along a nearshore to offshore transect with stations at 15, 45, and 110 meters. And it's located off Muskegon and Grand Haven area. For this talk today, though, to expand the spatial scope, we have data from other agency collections as well as some of the CSMI data that was collected in 2015. So special thanks to the USGS, the EPA, Michigan DNR, NOAA partners, and Buffalo State College for helping provide some extra data for this talk. Just to start out, just as a backdrop, and because it has had an influence on some of the things over the last 5 years, this is some data from our thermistor moorings in the offshore that are out over winter. And it's just kind of a reminder, during the last 5 years, we had two really, really cold winters, and you can see how severe that winter of 2013-14 and 2014-15 were. We also had a relatively mild winter. That 2011-2012 winter was extremely mild. You probably are aware how mild this past winter was. We've been out a few times already in March, and so the temperatures in March are around 4 degrees already. So that's pretty mild. So we're closer to what we saw in 2011-2014. So we shouldn't have any of the severe winter characteristics that we had the last couple years. Because of our seasonal sampling, we're able to see how some of the seasonal patterns in the lake have been changing over time. And this is nowhere more evident than in the chlorophyll in the offshore region. Historically, chlorophyll would have peaked in the spring, around May, and that was our spring diatom bloom, and that was an important characteristic of the Lake Michigan food web. You can see now we no longer have high chlorophyll in the spring. In fact, it's the lowest period of chlorophyll during the whole year. In the summer, in the surface mix layer, we don't really see a big difference. There hasn't been a big change over time. And then chlorophyll continues to increase in the fall, just as it had in the past. So thinking about May, this data is the spring chlorophyll conditions and also the spring total phosphorus conditions. And this data is from May because that's when we would have seen the peaks. And you can see over the last 5 years, actually probably the last 9 years, chlorophyll and phosphorus have been fairly stable, but they're very depressed compared to what you would have seen in the 80s and the 90s. You also might notice that the chlorophyll declines are much more pronounced than the declines in total phosphorus, and that's pretty reflective of a dry-scented impacted system. And this is for the offshore, and this is your isothermal period. If we move into the nearshore, we have a little bit less data. This data is from Muskegon at a 15-meter station, and this station's located a couple miles south of where the river comes out into the lake, so it's not impacted as very much by the river plume. You can see there haven't been huge changes between 1996 and now in the chlorophyll or in the total phosphorus at this nearshore station. Lest we think there haven't been changes in the nearshore, though, we also had a station that we sampled a little bit in the 70s in 1996, and then we've started revisiting that station off Grand Haven. So this station's in 15 meters of water directly off Grand Haven, so it is influenced by the Grand River plume. And you can see in 1996 where we had really high chlorophyll and phosphorus in the spring into the early summer, then it declines in the summer through the fall. We don't see any chlorophyll anywhere near or phosphorus like what we saw in 1996 at this station. And it's really hard to imagine a chlorophyll now in Lake Michigan that would approach 30 micrograms per liter. So there have been big changes in places in the nearshore, especially where you're influenced by a drowned river. And considering the importance of the Grand, this is probably a substantial result here. Like I said, when we move into the summer, the lake stratifies, and in that summer mix layer up in the epilimnion, we haven't seen huge changes in chlorophyll over time. But where we have seen changes in the summer is in the deep chlorophyll layer, and that's a layer that's subepilimnetic, and we define it as where the chlorophyll is greater than 2 micrograms per liter. So sometimes you'll have an elevated chlorophyll in the metalimnion, but it won't be more than 2 micrograms per liter. So just by this index, it wouldn't register. But you can see the deep chlorophyll layer has declined quite a bit compared to the 80s and 90s. One thing that did happen over the last 5 years is we had a huge influx of nutrients in the spring of 2013 in this region. And it's somewhat surprising, but you could see through our seasonal sampling, those nutrients make it out into the offshore. And we did have a substantial deep chlorophyll layer relatively in 2013. But for the most part, this deep chlorophyll layer is much reduced compared to what it had been. Another thing that we can look at is a nutrient limitation indices, and there's quite a few of these, but one of them is the carbon to phosphorus ratio. And you can see here, and this is for our 1545 and 110 meter station in the spring, in that summer surf mix layer, and then for the deep stations within that deep chlorophyll layer. You can see at the nearshore station, it's much less nutrient limited than at the 2 deeper stations. And it's a little bit more nutrient limited in the summer than in the spring. And probably neither of those things is all that surprising. At the 2 deeper stations, you can see that in the spring, in the summer surface mix layer, and in the deep chlorophyll layer, we saw severe, very, very nearly severe nutrient limitation. Now, thanks to extra sampling that was done by USGS as part of the CSMI program this year, we can take our Muskegon and Grand Haven data and put it into a little bit broader context. So this is the chlorophyll from an offshore and a nearshore station in the spring at the Muskegon and Grand Haven stations, and then 8 additional stations that were sampled by USGS. First of all, looking at the offshore on the top, you can see there's not a whole lot of difference among these stations, and chlorophyll is relatively low at all these stations. It's on the same axis as we have for the near shore. And that sort of reflects what we've seen over the last 9 years, 10 years, is where you have a homogenization of the offshore that we think is resultant of the mussel filtering, where it doesn't matter that much where you are in the offshore, it's not going to be that different from anywhere else. In the near shore, on the other hand, you see quite a bit more variation, with the stations in the southeastern part of the lake having elevated chlorophyll in the spring, and that's probably not all that surprising. The other thing I'd like to point out here is you'll notice a lot of the nearshore stations, especially in the northern part of the lake, actually have lower chlorophyll than at the corresponding offshore station, and that's maybe somewhat counterintuitive to how we think of the lake sometimes. Next, looking again at these same stations in the summer, in the summer surface mix layer. Again, in the offshore region, there's a little bit more variation in the summer than we saw in the spring, but really no meaningful variation among the sites. In the near shore, a little more variation again than we saw in the spring, but again, fairly elevated chlorophyll at our Muskegon and Grand Haven sites compared to the other areas of the lake. So at least for the near shore regions, those Muskegon and Grand Haven stations probably provide kind of an elevated sense of the productivity compared to other regions. But in the offshore, it probably doesn't matter so much where you're looking at your data from. One of the things to get at how different things are impacting the lake is using models. And Mark Rowe is an NRC postdoc at GLERL right now, and he's developed a 3D biophysical model to look at how things like mussels and loading interact to affect the lake. And this is data from the spring. On the far left, you have the satellite-derived chlorophyll. So that's kind of the baseline for looking at the model. Going right, the next one is the model results. I'm not sure I can't see it. There. The model results if you take into account current phosphorus loading and the mussel biomass in the lake and the mussel filtering. And you see that matches the satellite-derived chlorophyll pretty well. The next one over is if we take the mussels out of the model and we just have our current phosphorus loads. So if you compare that to the one we just looked at, that's your mussel impact. And you can see if we took the mussels out, even with our current low phosphorus loadings, we'd basically have our spring bloom back. And this would look like a satellite map of the chlorophyll before we had mussels. If you go to the next one on the far right, this is our phosphorus impact. So we put the mussels back in the model and you take the phosphorus loads out. And you can see not much goes on in the offshore region, but we lose all that nearshore productivity that you see in the baseline or the mussel and phosphorus map. So that if you take the phosphorus loading out, that phosphorus loading is what's supporting the nearshore production, it looks like. So this model is pretty powerful, and you can look at vertical slices of the water different times of year too. And so there's a lot of interesting scenarios that Mark would be able to explore with a model like this. So keep that in mind. Next, we'll move into the zooplankton. This is the mean annual zooplankton biomass across all months of sampling for the offshore and the nearshore station. First on top for the offshore station, you can see over the last 5 years, zooplankton biomass is suppressed compared to what it would have been in the late 80s, early 90s. But since the mid to late 90s, it isn't really all that different. One thing that did happen is the last 2 years, 2014, 2015, we had really low annual zooplankton biomass in the offshore. And we think that's related to that cold water temperatures. It took a long time for the water to warm up. And you can see we have very little Daphnia. They just got started so late they didn't have time to build up a very large population. So I think the cold weather is the reason we see such low biomass the last 2 years in the offshore. In the nearshore, the data doesn't go back as far. Over the last 5 years, it looks like we're still a little bit suppressed compared to the late 90s, early 2000s at this nearshore station. But what's really interesting is there hasn't been that much difference over the last 5 years. There's almost no variation. Even with that cold weather, it didn't seem to affect the nearshore station as much. And that's really surprising. The nearshore station is really, really variable. And for all aspects of it, these nearshore stations are susceptible to all sorts of disturbances. They're hard to get a handle on it. So to see something that consistent over 5 years is fairly surprising. We also can take a little bit broader perspective. This is the EPA sampling. This is the August data from the lake-wide surveys. And it only goes through 2011, but you can see how since the late 90s through relatively recently, it's been relatively stable zooplankton biomass in the offshore. This matches the Muskegon offshore data for the most part. One thing that we do see a difference in is in the absolute levels of biomass, and I think a lot of that comes from that everybody that does zooplankton uses different length weight regressions. So that's one of the things that the lower trophic task group will be looking into to make sure as we combine data sets that we're all comparing apples to apples when we do that. A time period that's really interesting for fish recruitment and also for young fish that are coming out of winter is the late spring, early summer period when you have larval fish appearing and fish are starting to feed at a faster rate again. So this is the May, June, and July data for the last 5 years at the offshore and the nearshore station. And I was hoping there'd be some really eureka types of things in here related to what we've seen in fish recruitment. I don't see them, but it's an interesting time period nonetheless. A few things that are interesting I thought were in 2015 at that nearshore station, even though we really had quite cool temperatures this year, we had fairly high zooplankton biomass at that nearshore. And we did see, at least at Muskegon, fairly good recruitment for a number of species in 2015, so maybe that helped play a part. But you see in 2011 we had fairly high zooplankton biomass in the nearshore too, and I don't think that was all that spectacular of a year for recruitment, so other things come into play. The other thing to note is 2012, even though in the nearshore we didn't have real high zooplankton biomass, we did in the offshore, and in both the nearshore and the offshore in 2012, we had a lot of cladocerans, and cladocerans are like candy for small fish. And so maybe related to the warmer temperatures that year, that played a part. So sometimes maybe it's not the total zooplankton that's important, it can be the types of zooplankton out there as well. So it only gets more complicated, I guess. Next, moving into predatory cladoceran biomass. There's 4 predatory cladocerans in the lake. 2 are invasive, Bithotrophes and Cercopagus. 2 are native, Polyphemus and Leptodora. On the top, we have the offshore region. And I just wanted to show that when you think of early in the summer, when a lot of times you have your larval fish, there really aren't that many predatory cladocerans in the offshore region. And the offshore region is mainly a Bithotrophy story. That's the main predatory cladoceran off there. They don't show up usually until late in the summer, and their peak is usually in the fall. So whatever impact Bithotrophes are having on fish, that's when it would be, late in the summer and in the fall. In the nearshore, it's a different story. Early in the summer, it's a Cercopagus story. And they're the most abundant predatory cladoceran there for the most part. And they eat really small prey, so they could be a competitor with larval fish during that period. Bithotrophes don't really show up in the nearshore until the fall, although when they do show up, they can reach pretty high numbers. Another thing that we saw in 2014 and 15 was fairly high numbers of the 2 native predatory cladocerans, Polyphemus and Leptodora. We don't really have an explanation for that. Looking at the mean annual biomass of the predatory cladocerans, you can see we were running at fairly elevated levels compared to the late 90s, early 2000s, until the last 2 years in the offshore. And much like we saw with the offshore zooplankton, the predatory cladocerans got set back by the cold weather in 2014 and 15. In the nearshore, that didn't seem to have an effect, and actually over the last 5 years, predatory cladoceran biomass built up, in part due to the Polyphemus and Leptodora increasing in numbers over the last 2 years, and then a huge biomass of Bithotrophes that we saw in 2015 in the fall. Now, one thing I want to take a look at now, just to give us a different perspective, all our zooplankton data is coming from vertical net tows. As part of the CSMI sampling, Hank Vanderploeg and his team at NOAA did optical plankton counter surveys with the plankton survey system from nearshore to offshore at Muskegon throughout the year. And so it gives you a little bit different perspective and gives you an idea of some of the spatial variability in a different scale than we sometimes think about. A couple things to highlight here is you see in May and June where that zooplankton biomass builds up in the nearshore and it kind of moves offshore along with the thermal bar. Once the summer stratification sets up, the other thing that we notice is most of the zooplankton biomass is centered in that metalimnatic region. It's not up in the epilimnion for the most part, it's in the metalimnion. And that biomass builds up and is really highest in the September, October region, and that's when you have your largest zooplankton out there. Another thing to keep in mind, again, when we think about these vertical net tows, especially offshore, when you're dropping a vertical net from surface to the bottom in 100 meters of water, you're running that net through probably 2/3 of the water column that has almost nothing in it, and then through really high concentrations of zooplankton in the metalimnion. So keep that in mind. They're not evenly distributed from the top to the bottom when we provide these numbers. So you could get a spatial mismatch vertically if fish aren't hanging out in the right area of the water column as well. Next, moving into some of the more benthic-oriented animals and macroinvertebrates. This data was provided by Ashley Baldridge. She's our new benthic ecologist at GLERL, replacing Tom Nalepa after he retired. And there's a Southern Basin survey that's done every year. I think it's 40 sites. And this is the number of sites over the last 5 years where dipraia has been found, and it's down to 1. And it's that mid-depth station out in the middle of the Southern Basin. Including that Southern Basin survey and then some data from the central and the northern part of the lake that was done as part of the CSMI sampling. We can look at dipraia throughout the lake. Some of the northern and central stations aren't counted yet, so the numbers of stations where you find dipraia might increase, but overall there's no reason to think that the overall story is going to change. There's very few sites. You can see all the dots that represent sites, and then you see the 7 where dipraia were found. And at these stations, dipraia abundance is very low. It was less than not much more than 1,000 per square meter at the highest station. When you think about most of these sites would have had diparia 20 years ago, and your densities would have been 5,000 to 8,000 at a lot of them, that's a huge change. Next, looking at mysis, this is data from Muskegon at our 45 and 110 meter site. We see over the last 9 years, numbers have been depressed to compared to what we saw in the 90s, late 90s at both of these stations, although we did see a substantial uptick in 2015 compared to the lower numbers that we'd seen the previous few years, but relatively no huge rebound or continued declines. It's interesting if you compare the numbers of mysis at these stations to what you would have seen in this area in the 80s. The numbers aren't that different compared to the 80s, but it's important to remember in the 80s, these mysis were supported by high productivity, and there were a lot of fish in the lake. Now we have the same number of mysis, but under low productivity and low fish abundance. So two different ecosystem paradigms are giving us relatively the same number of mysis. This is data from a little bit more of a lake perspective, and this is provided from the acoustic survey when they do some mysis. So this is from Dave Warner and Randy Claremont. And again, you can see no huge changes in mysis over the last 10 years. But again, if you compared the numbers to a lake-wide basis to the 80s, it's not that different, but under different ecosystem conditions. You'd expect mysis to rebound when fish numbers had declined, but they haven't. This is just to give you kind of a perspective using a few years of data on what that diparia decline means. And when you look at the biomass of diparia that was in the offshore, and that's not even your highest region of diparia biomass, compared to now when there is basically none, it really dwarfs some of these changes that we see in mysis and zooplankton. You could have pretty big changes in mysis and zooplankton in the past, and it would have made much of a difference because you had so much diparia. When you take that diparia out, you have a huge biomass that's missing. And we talked about in the Lake Huron group what's changed. This is a huge change that's happened in these lakes. Next, moving into the looking at some data from the quagga mussels. First, starting out back into a pelagic stage, we look at the veliger numbers. I'll say veliger biomass isn't a huge part of the biomass of zooplankton out in the lake, so they're not like a huge player in overall our zooplankton biomass. We had seen at all our sites declines in veligers, but then in the last 2 years they've rebounded. However, it doesn't necessarily mean that we've seen increases in recruitment of mussels that have been able to make it from the veliger state. So we're not quite sure how to use veliger data yet, what it really means in terms of mussel recruitment. It's kind of a tricky thing yet, but it is disappointing to see their numbers rebound. Next, looking at quagga mussel data. This is from Ashley, and this is from the Southern Basin Survey. Actually has the zebra mussels in there too. They're no longer a player. And you can see that black line in the middle is the weighted mean biomass of mussels. And you can see the mussel biomass in the lake has fairly stabilized over the last few years. A big reason for that is that 30 to 50 meter zone was the highest biomass of mussels that we had. And you can see how that's declined pretty dramatically and is for the most part leveled out. The one thing that's going on though is that red line, that's the greater than 90 meters. And you see that line over the last 5 years, that biomass is still increasing. And the area of the lake that's greater than 90 meters is a pretty big area. So it's a little concerning that the mussel biomass is still increasing, even though it's fairly low in that offshore region. The other interesting thing is all those regions that mussel biomass is sort of converging. So maybe we're hopefully getting to that point where we're going to be stabilized, but the offshore is a wild card. One reason why is if we look at the size distribution of mussels, you can see at a 45 meter station, where we had historically had the highest biomass of mussels, that population of mussels is mostly large, mature mussels, and we're not getting a lot of recruitment of new mussels there. On the other hand, on the right, we see time series at the 110 or 100 meter station. That's mostly small mussels. And for a while we thought maybe they aren't growing, they're not surviving into the larger size classes, but you see them very, very slowly starting to fill up these larger size classes. It's hard to see, but they are growing and we are getting larger mussels. So it's just taking a long time, which isn't surprising. It's cold and there's not a lot for them to eat in the offshore, but they do seem to be surviving and they seem to be growing. So it's possible the offshore mussel biomass could be a slow burn, and it could take a long time yet for it to reach where it's going to reach. We really don't know yet. So overall, the last 5 years were sort of uninteresting. We didn't see huge changes in most things. That's probably good news. The bad news is most of the characteristics of the food web remain at a suppressed level compared to what we would have seen in the 80s and even the 90s. So even though things haven't changed much, we still are in a suppressed level. And for a lot of these things, we would have expected them to increase given the low fish abundance in the lake. You would expect some of these things to show a rebound, and we haven't seen that. So in some sense, the paradigm of how things work with the lower food web has changed over time. And I'm happy to take any questions if there's time.